Hi, this is Alfozia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is concavity and inflection points. First, let us start with concavity of a function. The graph of a function in some region can be concave. I mean concave up, as for the point A, or convex, I mean concave down, as for the point B. Around a point in a concave region, the slopes of the tangent increases and the curve is above the tangents, while the slopes of the tangent in the convex region decreases, the curve is under the tangents. Am I right? At the point I, the concavity changes the direction. This point is called the inflection point. Do you understand the difference between concave, convex and the inflection point? At this point only, the direction changes. Hope you are clear with these terms now? Okay, now let us see the definition of concavity of a function. We use second derivative of a function to determine the shape of the graph. Let us start with the first definition. Let f is a function. It should be differentiable on the neighborhood of the point C in its domain. If the second derivative of the function at the point C is greater than 0, then the graph of the function f is concave at that point. The x-coordinate be c and the y-coordinate be f of c. Same way, if f double dash of c, I mean the second derivative is less than 0, then the graph of the function f is concave, convex at the point c, f of c. So if it is less, it is convex. If it is greater than 0, then we say that the function is concave at that particular point. So this is the first definition on the concavity. Now let me give you the other definition. So far we discussed two cases, if the second derivative is greater than 0 and less than 0. Now let's consider the third case. If the second derivative of the function at the point C is equal to 0, or you can say that the second derivative fails to exist, then the graph of f is either concave or convex, or neither two of them. Hope you are clear with this definition too? Okay, so far we were discussing the basics. Now let us see some solved examples. Here is an example. Please consider this function. F of x is equal to 2x cube minus x plus 1. Now we have to check at which point the function is concave and convex. Okay, to find that, as per definition, we need to find the second derivative. Okay, let us start with the first derivative. To find the first derivative, we will be applying the power rule, and for this one, it will turn into 1. And if you find the derivative of the constant, it will just vanish because it is equal to 0. So the first derivative of this function would be. Same way, let us find the second derivative. Second derivative is 6 times 2x, which is 12x. Now, let me take few points. I'm going to take a 0, a positive number and a negative number in the place of C and check whether it is positive, negative, or whether it is a transition number or not. Okay, at the point C equal to negative 4, let us check. All we have to do is replace the x by negative 4 in second derivative and check what number we are getting. So if I replace negative 4 in this place, negative 4 times 12 is negative 48. It means it is less than 0. So at this point, c equal to negative 4, the function is convex. Am I right? If it is less than 0, we say it as convex function. Hope you are till this point. Okay, now let us check the same function second derivative at the point c equal to 0. So what will happen if you replace x by 0? It will just be equal to 0. Am I right? F double dash of 0 is equal to 0. So it means at this point we can say that this function is this point is a transition number of the function f, because it will change the second derivative equal to 0. Hope you are clear with this concept, transition number. Okay, now I'm going to take a positive number and check what value will I get if I replace x by that number. For example, let me take c equal to positive 2. If c is equal to 2, f double dash of 2 is plus 24. Yes, it is a positive number. It means it is greater than 0. So if second derivative of the function is greater than 0, then we say that the function is concave at that point. Hope you are clear with this example. We have taken 3 points to check the concavity of the function. To find the concavity of any function, we need to find the second derivative. So in this problem, we found the second derivative, and in the place of x, we chose 3 points and plugged in those points one by one and checked whether the second derivative is greater than 0 or less than 0 or equal to 0. So depending upon the sign, we are saying at which point the function is convex, concave, or it is just a transition number. Okay, let me show you one more example. Here is the second example. Previously, I took an expression which is just like a square, I mean the quadratic function. Here I have taken an example where it has a denominator. So let us find the first derivative and second derivative, because whenever you are asked to find the concavity, you should find the second derivative. Only then you could assume some points and plug it in that point, I mean the second derivative, and check whether it is convex, concave. Okay, here the first derivative would be negative 1 over x square. You could also rewrite this function as x raised to negative 1, or you can consider this function as it is and apply the rule. So second derivative will be, please notice that the variable is in the denominator's place. If you plug in 0 in the denominator, it will, any number divided by 0 is nothing but an infinity. Am I right? So f double dash of 0 will be something infinity. Does this make sense to you so far? Hence, at the point 0, the graph of the function f is neither concave upwards nor concave downwards, because f double dash of 0 does not exist at all. Hope you are clear with this example? Okay, cool. Now let us move on to the next topic, transition and inflection point. In the first example itself, we saw a transition number. Let me give you the definition. From the name itself, you can understand transition means it is just a transformation between something two. So transition is in between the concavities, upward or downward. If the point C is in the domain of the function f and f double dash of C, I mean the second derivative of the function at the point C is equal to 0, or it may be this other case. Hope you remember the second definition. If f double dash of C fails to exist, then the real C is called the transition number of the function f. Hope you are clear with this definition now? Okay, let me take one example and explain you. I have taken a polynomial. Okay, so in order to find the concavity, you should find the second derivative. Okay, let me start with the first derivative. First derivative will be 8x cubed minus 3x square, and the third term vanishes because it does not have any variable. Now let's find the second derivative. Second derivative is, again we are going to apply the power rule. 8 times 3x square, 3 times 2x. So f double dash of x is be 24x square minus 6x. I'm going to set this x is equal to 0. So if I set x is equal to 0, x has been multiplied, no? So obviously this will turn into 0. 24 times 0 square minus 6 times 0 is 0. So with x is equal to 0, you can also take a common factor outside and do the quadratic, what we do in factorization, because this is a quadratic function, right? So I'm going to take the common factor out first. The common factor between these two is 6x. If I take it out, if I replace the left side by 0, I'll get some factors on the right side. Hope you all are familiar with the very popular rule. If a product is equal to 0, then you can equate each of the factor to 0 and then solve for x. Here I'm going to do the same concept. So if I set the left side equal to 0, equate each of the factor to 0. So solving for x, I'll get x is equal to 0 and x is equal to 1 over 4. The points c is equal to 0 and c is equal to 1 over 4 are included in the domain of the function f. Their second derivative are 0. Then they are the transition numbers of the function f. That's it for this example. Hope you're clear with this concept now. Okay, now let us move on to the next topic, concavity on an interval. Here we are going to talk about a differentiable function. on a closed interval a comma b. Let f be a differentiable function on an interval a comma b for any x in that interval a comma b. If the second derivative is greater than 0, then the graph of the f is concave upwards in the whole interval a comma b. If the second derivative is less than 0, then the graph of f is concave downward in the whole interval a comma b. Hope you are clear with this definition. In case if you get any query regarding the topic that we discussed in our today's video, please let me know. See you in the next video. Have a great time ahead.